Today's topic, as I mentioned, is radioactivity and atomic structure. The item in red, the atomic structure, we're actually going to do that first. And once we understand atomic structure properly, I will be able to explain this thing called radioactivity. A lot of you all may have heard the word radioactivity from your superhero movies. That is how the Incredible Hulk from the Marvel Universe became the Hulk, due to something called radioactivity. So let's move on to the first slide here. I think everyone has a pretty okay idea of what an atom is, right? An atom is one of the smallest structures. Here are the key words. It's not the actual smallest structure, but an atom is really, really small. And it's made up of other particles. The particles that make up the atom are something called protons, neutrons, and this guy down here, something called electrons. In case you all forgot, right? Protons have a positive charge. In case you can't, relate to that, you know how a battery, like those regular Duracell batteries or ever-ready batteries, how they have a positive side and a minus side, a negative side? Well, guess where those charges come from? They come from things like protons, which have a positive charge, and electrons, which actually have a negative charge, or some people just call it a minus charge. There's also something called a neutron. A neutron has no charge, meaning that a neutron is neither positive nor negative. What a lot of people don't know is that protons are at the center of the atom. So I have a little colorful diagram here. Everything in red is a proton, and protons have what charge? A positive charge. The neutrons are also at the center of the atom. And I use blue to kind of depict the neutrons. And neutrons have no charge, meaning once again, they are neither positive nor negative. The electrons, on the other hand, are not at the center. They revolve around the center, just like how the planets revolve around the sun. And the electrons, and there are many of them usually, and all of them, all the black dots, have what? A negative charge. It's very important to note that the center of the atom, which contains the protons and the neutrons, that entire section is called your nucleus. And your nucleus has an overall positive charge, because at the center of the atom, there are protons, which are positive, and there are neutrons, which have no charge, which means the positive has no competition. So the center of the atom at the end of the day is positive. This is how we view the modern atom, meaning that a few hundred years ago, did you all know that we did not know that the atom was actually made up of smaller particles? In the 18th and 17th century, scientists did not know about protons, neutrons, and electrons. And the first part of the syllabus is that we have to go through the history of the atom and see how the picture of the atom developed over time. So I'm going to give you all 2 minutes to take down anything you need on the screen. And after the 2 minutes, it's up. We're going to move ahead. You'll notice on the screen, I have the word shells, but I did not discuss the word shells. The shells is the orbits around the nucleus. It's the path that the electrons take around the center of the atom. Each one of these orbits is called a shell. So this particular atom in front of you, how much shells does it have? Real simple question, not a trick question. How many shells does this atom have? It would be 3. This circle here or this orbit is 1. This is the second one, and this is the third one. Different atoms have different amount of shells. Some people call them shells. Some people call them orbits. I prefer to use the word shell. Right? Now, here's another thing. Protons and electrons are supposed to be equal, right? So let me put a note here that's going to be important. Protons and electrons are supposed to be equal. That means if an atom has 5 protons, 5 positive charges, it's supposed, keyword, it's supposed to have 5 electrons, which are negative, to balance it. So if an atom has 10 protons, it's supposed to have 10 electrons as well. Neutrons, on the other hand, he's the wild card. He doesn't listen to anybody. An atom can have a different amount of neutrons when compared to protons and electrons. The only thing that is usually required to be equal is protons and electrons. Right, so I think that's about 2 minutes there. So we're moving on to the next screen. Remember I said, if and everyone will get accustomed, if you're not finished taking down everything, you could always take a quick screenshot and finish it out for homework. All right, so moving on to the next slide. All right, so let's go back to the 1800s, okay? There was this guy called John Dalton. He was interested in the atom, but remember back then, there weren't powerful microscopes and sophisticated equipment to kind of figure out how an atom actually looks. John Dalton came up with these theories here. Now, it's going to take a while to discuss all of these, right? But let's number them. He said 1, 2, 3, 4, 5 things about an atom. Some of these things he said about the atom are true, and some of these things he said were not true. He wasn't lying on purpose. It's just that he did his best, given the equipment he had. I want everyone to take down all 5. And then I'm going to ask you, from your knowledge, which ones from the 5 are true and which one are false. But take down the note first. Take down the scientist's name, because in the exams, one of the most important questions they just ask you, John Dalton, what did he say about the atom? And you will have to list all 5 things for the examiner. It's almost like a history lesson. Right? So I'll give you a 2 minutes to take down everything on the screen, and then we will discuss which ones are true and which ones are together. The first one, let's do this together. Do you all think the first one is, oh, before I get to the questions, this is what John Dalton basically taught about the atom. Look at this red diagram here. Look how boring and dull that is. John Dalton, right, taught an atom was just a ball, a very, very small ball. He did not know anything about protons, neutrons, and electrons. That was beyond him. So number 1, do you all think you all could say that statement is true? Elements are made of extremely small particles called atoms. Yes, I would say this is true, because that is true. Everything, including your body, is made up of smaller particles called atoms. How about 2? Atoms of a given element are identical in mass and other properties. True or false? right? Now, some of y'all might be saying, you might have problems processing the statement. This is actually true. Let me explain why, okay? Let me explain what this is saying in simple language. I think everyone here at some point in time would have seen something called the periodic table. It's in front of you right now. So let me make it a little bit larger for you. A periodic table are all the elements that are found in on planet Earth. It have things like hydrogen. Look at it here. Things like hydrogen, lithium, beryllium, magnesium, sodium. What the second statement is trying to convey is that he's trying to say that if you have an atom that's hydrogen, a very, very common atom, he's trying to say all hydrogen atoms have the same exact size. He's also trying to say that sodium, which is a different atom, might be a little bit larger than hydrogen. But all the sodium atoms in the universe have the same exact size. That is what he is trying to say, right? That if you pick an atom and you go anywhere in the universe and find that same type of atom, it will have the same exact size. So statement 2 is actually true. What about statement 3? Atoms cannot be subdivided, created, or destroyed. That's definitely false. Whenever you say an atom cannot be subdivided, they're really trying to say that an atom is not made up of smaller parts. But we know that is false now, right? We know that atoms are made up of definitely smaller parts, protons, neutrons, and electrons. So I'm putting an F here for false, right? How about number 4? Atoms, that's that one, I'll read it here. Atoms of different elements combine in simple whole number ratios to form chemical compounds. True or false? That's actually true, right? I'm not going to go into detail about why this one is true, right? It's basically this. I think everyone knows something called water. Water is H2O. Water will always be H2O, meaning that there will be 2 hydrogen atoms and 1 oxygen. So the ratio is 2 to 1. The 2 stands for 2 hydrogens. The 1 stands for 1 oxygen, right? I'm not going to move too much into it. You just have to remember this one, that one is true. And this one here is also true. So the only false one is 3, right? So make sure and write it next day in nota, which one is true and which one is false. It can come in your exam. Take 20 seconds, take down what you need to take down, and we will move on the list. All right. So John Dalton, that was his theories. Let's see who's next on the list. The next person on the list was this guy called Joseph John Thompson. And we're talking about roughly 1897 here. Now, Mr. Thompson did a slightly better job at coming up of the picture of how the atom actually looks. But was he correct? Look at this diagram. He came up with the theory that an atom is a big positive ball, and living inside the ball, right? Living inside the ball are negative charges. That's definitely not correct, because we know how an atom is. An atom is supposed to have a center and revolving around it, or orbiting around it. It's supposed to have the electrons. Over here, the electrons are literally inside the atom. But at least he came up with the idea of what? The electron. The guy before didn't even know anything about electrons, but Mr. Thompson, you could give him some credit for that, okay? So I want you to take down everything on the screen, except obviously for this note and this note, right? And they call this this diagram here, the plum pudding model. That was his nickname because it does look like a plum pudding pie. So please let me know when you're finished with everything on the screen, including the note. For the exam, you have to memorize everything there. Let's move on. Let's see who's next on the list. Next on the list is this guy in 1911, Ernest Rutherford, who's probably one of the most famous scientists out there. Now, Rutherford looked at other scientists' work, just like other scientists, and built on what they had already learned, and was able to come up with a better picture of the atom. Look at this picture of the atom, and I want you all to tell me what is missing. At the center, there are positive charges, and revolving around it are the electrons. Who can tell me what two things are missing? Jeremiah, correct. Chelsea, correct. Nikolai, correct. Samantha, Siddiq, correct. Haley. Right, again, a lot of great answers. You all will realize that the neutron, the item with no charge, is missing. So Rutherford did not know about neutrons, but at least he figured out that the center of the atom was positive, which kind of hints that he knows about protons. Also, the electrons are revolving around the atom, the center. But if this is the center of the atom, which is positive, and there's supposed to be shells, notice there are no shells, but at least he figured out that the electrons was at least going around the center. All right, so we have to give him his credit. He did a brilliant job. All right, here and later on, we're going to discover, right? We're going to kind of figure out or look into how Ernest Rutherford figured out that the center of the atom is positive. So I want everyone to take down the notes, and I want to put a question towards you all. Look at the year this guy was living in, around 1911. There were no powerful microscopes, definitely nothing powerful enough to see an atom clearly. How do you think he figured out that the center of an atom is positive without being able to see it? I want you all to think about that. So after you think about it, let me know how you might have gone about trying to figure out that a center of an atom, something so ridiculously small, is positive without actually being able to hold it or see it. So let's move on now, because we still have other things to discover about the atom, the shells, the neutrons. So let's see who did this in history. Next on the list is this guy called Niels Bohr in around 1930. He was a guy who did experiments to figure out, look at his model. He knew that the center was positive, and he figured out that the electrons were revolving around the center, but in orbits, also known as shells. Okay? So everyone take down the note. I'll give you 2 minutes again, and we're going to move on. So let's see about the neutron now. Moving on, and the trophy for the neutron goes to James Chadwick in 1932. All right, so now we have a complete picture of the atom. We have protons, which are positive, the neutrons, which have no charge, and the negative electrons revolving in orbits around the center. So take down the note, 2 minutes as usual, right? All right, so one person is asking me to go back and check. I don't know why. All right, so let's go through some basics here now. I'm not going to spend too long on this, right? I'm not going to spend too long on this because we'll be covering this in chemistry also. Whenever you have an atom, right, and you go on the periodic table, like if you go and see something like oxygen, right? Let me give you an idea. When you go to the periodic table and you look at any element, you will see two numbers, all right? One number will be larger than the other. And of course, I need to show you what these numbers represent, right? So whenever you have an element, let's just call it X. X can be represented any element, oxygen, nitrogen, whatever it is. Usually there's a number on top and a number underneath. That is being represented by the letters A and Z. The bigger number, you just call it the mass number, and the smaller number, which is represented by the letter Z, is called the atomic number. The atomic number always tells you how much protons the atom has. The top number tells you the amount of protons plus neutrons. Now, this is always confused students, right? So anytime I have to teach this, I actually have to use a picture of a real atom. So everyone look closely over here. Keep your eyes focused here. Let's say this is an atom. Let's just call it X. Like I said, X could represent any element. A color-coded field. What number do you think I have to put at the underneath here? What number do you think will go here? Look over here. That's the Z value. Z represents the amount of protons. And in case you all don't remember, protons have a positive charge. So everything in orange is a proton. So it has 1, 2, 3. So the underneath number is 3. The top number, which is the mass number, is the amount of protons plus neutrons. So we have to add the protons and neutrons, right? And a lot of people are telling me the top number is 7. Let's just clarify that. Let's add up all the protons and neutrons. 1, 2, 3, and the green ones, 4, 5, 6, 7. Anytime you minus these two numbers, the mass number and the atomic number, 7 minus 3, well, in today we'll get 4. Whenever you minus these two numbers, you will always get the amount of neutrons, obviously. 1, 2, 3, and 4. So these numbers here, the mass number and the atomic number, the proton number, gives you information on protons and neutrons only. But don't atoms have electrons also? So how come they don't tell you how much electrons the atom has? It's almost like they're saying electrons not important, so we're not going to tell you how much electrons are present in the atom. But electrons are very, very, very important. The reason is protons and electrons are supposed to be what? Equal. So why waste ink? If I come and tell you that it have 3 protons, then by logical deduction, it also has what? 3 electrons. 1, 2, 3. It's supposed to have the same amount of protons and electrons. Supposed to. So take down everything on the screen. You'll just be, you see this concept that's on the screen right now? It will only be mentioned once or twice later down in the tutorial, right? and I will gladly repeat what I just said in case you forgot. Take 2 minutes and we're moving on. All right, so let's go through some properties that you have to memorize for the exam. And boy, do students complain about this part here. Let's compare a proton, neutron, and electron. You see this first row? I'm going to actually explain that last. A lot of students have problems understanding what relative mass is, okay? Let's start off with relative charge. That might be easier to understand. A proton is what? Positive. We know that already. We know electrons are negative. So they usually say -1. Every electron that you hold or come in contact with has a relative negative charge, and the value is -1. And it is considered a proton +1. You notice that the neutron has no charge, so the value of its charge is 0. It's neither positive nor what? Negative. A proton, its mass, look at this mass here, 1.7 multiplied by 10 to the power -27. Huh? Do you all think that's heavy or light? They put the value in standard form. That's very, very light. 0.17 kilograms to this number is 0.000. It has 26 zeros in front of it. 17 kilograms. It's very, very, very light. Okay? You notice a neutron is also very light. It's almost the same mass as a proton. And the electron is even way lighter than the rest of them. The actual charge, right? I made a small mistake here. Charge is measured in something called coulombs. Capital C, which will be covered later on when we start electricity. Remember, protons have what? A positive charge. But if you ask me, what's the actual value of the charge? Like how much current does it have? This is the value you have to memorize. And for an electron, this is the value that you have to memorize. I want everyone to take down everything on the table, and then I will explain what relative mass is. I want you to understand the difference between relative mass and actual mass. Okay. So pay attention here. So relative mass, okay? Let's say I have a block, okay? And I tell you that this block is 2 kilograms. So that's the mass of the block. Now, I have another block, and I tell you its mass is 8 kilograms. So I'll call it block A, and I will call it block B. Block B is clearly heavier. I think you all could agree with that. But here's my question. How much times is it heavier than block A? Simple calculation. We know block B is heavier, but by how much times? Everybody is going to say 4, right? Because 8 divided by 2 is 4, right? So block B is 4 times heavier than block A. But let's use some technical language now. The block B relative, right? Relative means that's this word here, means you are comparing it to something else. So block B relative to A is 4 times heavier. So I kind of use the word relative in a sentence. So keep that in the back of your head, that the word relative means you are comparing it to something else. Okay? Now here's the thing, right? If I scratch off the 2 kilograms and I scratch off the 8 kilograms, and somebody now joins class, and I scratch off this also, and I only leave the relative value. So all the great information is missing, and the person now join class. And I tell them that block B relative to A is 4 times heavier. Do you think that person will be able to figure out the mass of A? Think about it. Pretend you now come to class, and all I tell you is block B is 4 times heavier than block A. They would not, how would they know how heavy either block is, right? Let me put that in perspective. Some people are saying, yes, they will be able to figure it out. All right, let's put that a different way. Let's have 2 people, new situation, a small person and a large person. And I tell you the large person is 5 times heavier than the smaller person. So relative to the small person, the big person is 5 times heavier. Would you all be able to reason out the mass of the small person? The answer is no, right? There's no way, because you don't know the mass of the foot of the big person. So you don't know what to divide it by. You have to take whatever his mass is, which we don't know, and divide it by 5 to get back the mass of the smaller person. Okay? So whenever you use the word relative, you don't know the actual masses. You just know who is the heavier one and who is what? The lighter one. And you know how much times heavier or how much times lighter. So tell me, which one do you all think is more useful? Knowing the relative mass or knowing the actual mass? Which one do you think will be more useful in a lab? Actual, right? Actual is always more useful, right? So let's look at this here. The relative mass. The relative mass of protons and neutrons is 1. This basically means that both the proton and neutron have the same mass, because relative to each other is 1, right? So none is really what? Heavier than each other. But the electron, when you compare it to either the proton or neutron, is 1,840 times lighter, which means electrons are way smaller when you compare it to protons and neutrons. All right? And the same thing goes for relative charge. When you're given a relative charge, you don't know the actual value of the charges. You just know one is positive and one, by comparison, is negative. Actual charges, to me, are more useful, the actual value of the charge. All right? So we move in. You don't have to take down anything there, right? Just keep that explanation in the back of your head, and let's move on. Right? Right, so this is the number 1 question everyone is asking. It's on the chat right through. People are saying, what, or asking, what is an isotope? And now we have the answer. Isotopes are forms of an element that have the same number of protons, but different number of neutrons. Now, I made sure I included a diagram here. Carbon. Carbon is a very popular element. You know which part you can find carbon? A pencil. The tip of your pencil is made up of something called, I know it's kind of hard to see here. It's made up of something called carbon 12. But here's the thing, right? Whenever students hear the word carbon, they just think it only have one type of carbon. There are many different types of carbon. The same thing with oxygen. There are different versions of oxygen out there. When you hear nitrogen, there are different versions of nitrogens out there. We call all of them carbon, we call all of them nitrogen, but the different types will have slightly different names. Here we have two different versions of carbon, something called C12, carbon 12, and something called C14, carbon 14. Now look at this. Everything in blue in this diagram is a proton. Let's look at both diagrams. The first one has 1, 2, 3, 4, 5, 6 protons. So I'm going to put 6 plus, meaning 6 protons. Carbon 14 also has 1, 2, 3, 4, 5, 6. So he also has 6 protons. But let's look at the neutrons now, the red ones. Carbon 12 has how much? 1, 2, 3, 4, 5, 6. It has 6 neutrons. Now it's only coincidence the protons and the neutrons are equal. Protons and neutrons do not have to be equal. Let's look at carbon 14 now. Let's count the amount of neutrons. 1, 2, 3, 4, 5, 6, 7, and 8. It has 6 neutrons. No, 6. 8 neutrons. Do you all see the difference there? Both of them have the same amount of protons, but have different amount of neutrons. They are both carbon, but one is carbon 12 and one is carbon 14. It is called this one carbon 12 because if you add up everything in the nucleus, you will get 12. 6 plus 6 is 12. And carbon 14, if you add up everything in the nucleus, 6 plus 8 is 14. And yes, I would really like it if you draw the diagram as well. Take down this note and draw this diagram to accompany it. Because this is one of the most popular questions in the exam, right? And you all notice that the amount of protons and electrons are the same. Both of them have 6 protons, and they have how much electrons? 1, 2, 3, 4, 5, and 6. Over here is 1, 2, 3, 4, 5, 6. Protons and electrons are always equal. Well, they are supposed to be equal. Right, so let me know when you're finished with the top note, right? The isotope and the diagram. Leave out the radioisotope. I want to explain that first before you write it down. All right, so by looking at the word radioisotope, right? It's made up of 2 words, radio, which stands for radioactive, and isotope. And I just explained what an isotope is. A radioisotope is an isotope that shoots out radiation. That same thing that turned the Hulk into the Incredible Hulk. And that's just one example, all right? Let me try to explain why something emits radiation. And in a lot of cases, radiation is something dangerous, right? Whenever you're exposed to this thing called radiation, it can cause things like skin damage. It can even lead to cancer and whatnot. Sometimes we have atoms. Let's look at carbon 12. Carbon 12 is what I consider to be a happy atom, meaning that he's comfortable with who he is. He has, let's look at his structure. He has 6 protons, he has 6 neutrons, and 6 electrons. Everything is perfect in his life. He's happy. But, right, let's look at carbon 14. The thing about carbon 14, he's not happy with himself. So something is wrong. Maybe he is sick or something. Let me give you an example. Let's say you buy a pizza, and the pizza it's spoiled, right? It was left out in the open for too long, and you eat the pizza. you would get upset. I think most people who eat spoiled pizza or spoiled food is going to get upset. Most likely, you're going to vomit it out. This is a gross example, but it will help you understand, right? So usually when you're sick or something is wrong, a common symptom is to vomit it out. Why are you vomiting out the food? To get rid of the food, because your body knows if you get rid of the bad food, you have a better chance of feeling better. Do we understand that concept? That the reason that you might vomit the food out is that your body is trying to feel better. It's getting rid of something. Atoms are almost the same thing, right? Remember, I just said that carbon 14, this particular atom, something is wrong with him. So what he will do, he will try to get rid of something. So something is wrong over here. So he will shoot out radiation, right? And hopefully when he shoots out the radiation, that's his version of vomiting, it will feel what? Better, right? So that there is the reason why atoms shoot out radiation, why some atoms are considered to be radioactive. But you're probably asking, but what made the atom sick in the first place? Like, what makes an atom sick? Let's look at these two reasons here. Sometimes, right, in most atoms, right, you see the amount of protons and neutrons, it have a certain ratio. Whenever atoms have too much neutrons, like it just have too much neutrons, it is make the atom sick. And when it's sick, it will try to expel something, get rid of something. And that's something it's getting rid of is called radiation. So, and another reason why the atom might be sick is that the center of the atom, the nucleus, has too much energy. You don't have to worry about why it has too much energy. That's not on your syllabus. But whenever a nucleus has too much energy, you just call it excited. Just like when a child, when they give him too much sugar to eat, right? He just get excited, right? He has too much energy in him, right? So for the exam, you have to know the two reasons why an atom might be considered, using these words loosely, sick, right? It becomes unstable, right? So a lot of people are going to ask how much neutrons, how much extra neutrons does it take to get an atom sick or unstable? That's not on the syllabus. Different atoms have different rules. So like I'm just saying, for iron to become unstable, it would require a different amount of excess neutrons than, let's say, radium. All right? Everyone have a general understanding of it, right? Oh, and whenever an atom is sick and it's shooting out radioactive substances, you just call that particular type of atom a radioisotope, better known as the sick atom who wants to feel better, right? Let's see what's next on the list here. Oh, we have a little animation here. All right, so let's talk about the different types of radiation, right? Now, there are two categories of radiation. Now, here's the thing, right? Whenever you talk to a student about radiation, right? Because you saw so much TV shows and so much movies, when you ask a student to name a type of radiation, the only type of radiation they seem to come up with is gamma. And once again, you have to blame, not blame, well, attribute that to comic books, because gamma radiation is the type of radiation that once again turned the Hulk into the Incredible Hulk. But there are other types of radiation there who should be put under the spotlight. There's one category called particle radiation. A particle radiation means it's an actual particle that you could, if your hands were small enough, you could actually hold it. I mean, really, 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 really small. You could hold it. A particle is something you can hold at some point. But then there's something called electromagnetic radiation. Electromagnetic radiation is not a particle. It's pure energy. So you can't hold it in your hand. Okay? So the symbol for alpha, and of course, you're probably asking yourself, well, what does alpha look like underneath the microscope? What does beta look underneath like in a microscope? I will get to that eventually, but let us just get the names correct. The two types of particle radiation are alpha and beta. The symbol for alpha is this symbol, and the symbol for beta is this symbol. These are Greek symbols. The symbol for gamma is a kind of funny looking Y, right? You can put a Y. The examiner not going to judge you too hard at it, okay? Now, for the CXC syllabus, and I have to keep stressing the CXC syllabus, right? Because remember, when you go in Form 6 or you go to university, you're going to learn a lot more about radiation than at the CXC level. For CXC level, we will only be talking about alpha, beta, and gamma when it comes to sick atoms. Remember, I told you that when atoms are sick, they shoot out things or get rid of things. And the three things that they get rid of are alpha, beta, and gamma. So those are the only three we're going to be discussing for radioactivity. The rest of these guys here, we will not be talking about them with regards to radioactivity. All right. So let me know when you're finished with everything on the table, but you have to take down everything in front of you, right? One person finished. All right, so you're not going to like this table here, but it's one of the most important tables. A lot of these things on the table are not going to make sense. So I want to talk a little bit about all of the complicated ones, right? Let's start with this here. Alpha, right? Alpha is something called, if you were to able to see alpha, let's say you had a real powerful microscope, and you were able to see alpha. Alpha is actually a fast moving helium nucleus. I will get into a detailed explanation about this just now. Beta is a fast moving electron, and gamma is something called a high frequency electromagnetic radiation. Let me explain this one first, right? I now said that alpha is a fast moving helium nucleus. So let's move to the periodic table, right? And you all will see something here, right? 1 second. Right. If you look on the table here and we slide across the periodic table, to the end, you will see something called helium. Tell me something. Is helium considered dangerous? Would you say helium is something that can harm human beings? The answer is no, it's not particularly dangerous. You know which part it is used, helium? You know those balloons that is float, right? They just put helium in it. Also, if you breathe in helium, you can breathe in helium, your voice will sound funny, like a cartoon character, okay? So at the end of the day, helium is not particularly what? Dangerous. So let me show you something. Let me draw helium, Let me draw a helium atom for you. A helium atom, one second, has 2 protons, 2 neutrons, and it must have electrons. Anybody can tell me how much electrons it will have? We're talking about helium from this diagram here. Right, it's supposed to have 2 electrons. So it will have 2 electrons circling around it or orbiting it. So over here is an helium atom. But helium is not dangerous. But here's the thing. Remember, the center of the atom is called what? Your nucleus. Keep that in the back of your head. Here's how we can make helium dangerous. Right now, it's not dangerous. If we take away the 2 electrons, so I strip that away and I strip this away, it's no longer, I don't think it's fair to call it a helium atom anymore. You know why it's not fair to call it a helium atom? Because the electrons are missing. So right now, this is a helium what? Nucleus, because it's not like we take away one of the electrons. We take away all the electrons and we only left the nucleus. Now, it's still not dangerous. To make it dangerous, we have to take the helium nucleus and speed it up. We have to make it move very, very fast. And whenever you take a helium nucleus and you make it move fast, you just call it what? Alpha. And alpha can be dangerous to human beings depending on how you use it. If alpha ends up inside your body, outside your body, it's not too dangerous. But if alpha gets inside your body, like in your stomach and whatnot, it can actually cause serious blisters and you will die from internal bleeding. So that is what alpha is. And that's what I'm trying to say in this sentence over here, right? Alpha is a fast, and I use the keywords, alpha is a fast moving helium nucleus. So someone asks, well, how do you make it move fast? The truth is, we don't make it move fast. Whenever an atom is sick, right, it will vomit out the alpha particles at a very, very, very high speed. And so the atom actually makes it what? Move fast. Human beings don't make it move fast. It happens naturally in nature in radioisotopes. Beta, I'm not going to give you a detailed explanation here. If you take an electron and make it move very, very fast, you see when sometimes atoms will spit out electrons, but it is do it very, very fast. You just call that what? Beta. It is shoot it out. And gamma, I'm not going to go too much in detail about the gamma. Just memorize this, something called high frequency electromagnetic radiation. This is pure energy. So everyone take down the first row. Take down the first row. Let me know when you finish with the first row only. I don't want you to take down every single thing and you're not understanding what you're taking down. Right? So I'm pausing it here. When you go to the school website, right, this is what you are going to see. It's a very, very, very simple website. Today's class recording, we're going to put it underneath summer recorded classes, right? So when you click over here, I haven't uploaded a video yet, but you will see it here by tomorrow. So in case you want to review today's video, and you want to go through it back and put in any little missing notes, you can, okay? The other thing is, for the summer, I not only want to do radioactivity and atomic structure, I want you all to learn a little more than that. So when you're on the school website as homework for next week, I want you to click on the physics classroom. Make note, you're going to click on the physics classroom. So I'm going to click on it. And when you click on the physics classroom, you will see a whole set of videos. I want you to watch this video. I'm highlighting it for you. Forces, theory, and calculations. Now, when you watch the video, just don't watch it. Watch it and make notes. If you don't understand something, rewind it. I explain it from basics, so almost anybody could pick up on it, right? Everyone understands that as the homework. And I'm going to put the homework here. You can screenshot the homework, the same thing I just said. Screenshot this so you don't forget what the homework is, right? So no one has an excuse of not knowing what the homework is. I said it verbally and I wrote it out for you. Now, I can't make you all do the homework. And of course, I'm not going to go and check your books, and I'm not asking you to send me the notes. But if you want to become a student who's better at physics and be super prepared for when school starts back, make the sacrifice now. All I can do is tell you and be a little encouraging. Hey, do your homework. But at the end of the day, it's up to you all if you all want to learn. Okay? Right. One other thing, right? Well, let me get this off the recording.